Hello. This is week 6 of the Mechanical Measurement System NPTEL course. This week dealt with transducers, flow measurements, and temperature measurements. So I have prepared some problems on those. So we'll start with some MCQs. The first one is the T-type thermocouple has the wires made of. So the T-type thermocouple has the wires made of A. Copper constant N, B. Iron constant N, C. Zinc constant N, D. Aluminium constant N. Sorry, so we'll repeat. So you have different types of thermocouple. So in this case, we have asked to the material of the T-type thermocouple. So the T-type thermocouple is been made of A. Copper constant N, B. Iron constant N, C. Zinc constant N, and D. Aluminium constant N. So as you know, yeah, the thermocouples are uh, classified based on their materials, and they are named as T, K, N, E, and there are some special types of thermocouples as well. So in this case, the T-type thermocouple is made of option A, copper constant N. And as you know, E-type is chromal and chromal constant, which is chromium nickel, and you have J-type uh, iron constant, and then other aluminum constant like K type, and some special which are made of platinum. So those are different types of thermocouple. So in this case, they ask T type, which is option A, copper constant. Then moving on to the next question, we have the fluid density does not affect the working of A. Orifice plate, B. Pitot static probe traverse, C. Rotameter, D. Electromagnetic flow meter. So the fluid density does not affect the working of, out of which A. Option orifice plate, B. Pitot static probe traverse, C. Rotameter, D. Electromagnetic flow meter. So as you know, orifices in the tube, you have a disc with a hole inside, so that is a kind of an orifice plate which is put in, it's an obstruction type, so that is an orifice type meter. And you have a pitot static tube, which your probe, you measure static as well as dynamic pressures, and you measure the difference which will give you the velocity. That is a pitot type measurement. And then you have a rotameter, in which a bob is placed inside a tube, and when the flow occurs, the bob will move, and you use that as the measurement. That is a rotameter. And you have electromagnetic, using the electromagnetic as a measurement. The flow meter, you measure the velocity, the change in the flow. So in this case, they asked, out of these are four, which does not get affected by the fluid density. So if you change the fluid, it should not affect the working of that. So in this case, the option is option D. So in this case, the density doesn't affect the electromagnetic flow meter. Rest of it will affect. If you see in the calculations of the velocity and other, you will use the density, so it will definitely affect the others. Moving on to the next question. So yeah, which of the following is not suitable for measuring the flow of a non-conducting flow? So option A, orifice plate; B, venturi meter; C, electromagnetic flow meter; D, rotameter. I think this is a fairly simple question. They asked the fluid which is non-conducting type cannot be cannot be measured. The flow of that cannot be measured using one of the options given. So you have orifice plate, B, venturi meter; C, electromagnetic flow meter; and D, rotameter. So we know that uh, electromagnetic flow meter cannot be used because you need a conducting medium for that magnetic field to be generated. So out of this, the option C is the correct one. Uh, the flow of a non-magnetic fluid cannot be measured using an electromagnetic flow meter. Okay. So moving on, we have next question. Which among the following is a constant head variable flow meter? A, venturi meter; B, lobed impeller flow meter; C, vane anemometer; D, rotameter. So in this case, you have they ask you have a constant head, and for a variable flow, which of the options is used? So in this case, the answer is option D, rotameter. Moving on, you have a positive displacement flow meters are of what are the positive flow displacement meters? The quantity flow meters, the constant area variable head meters, the constant head variable area meters, the variable area variable head meters. So in this case, the positive displacement flow meters are option A, the quantity flow meters. The positive displacement, you have net displacement of the fluid, so that's the positive displacement. So in this case, the positive displacement are the quantity flow meters. Option A. So moving on to the next question, we have in an orifice meter, the coefficient of discharge is. So I repeat, in an orifice meter, the coefficient of discharge is A, uncertain and can have any value; B, equal to the coefficient of discharge of venturi meter; C, more than the coefficient of discharge of venturi meter; D, less than the coefficient of discharge of venturi meter. So you are asked to compare the coefficient of discharge with the venturi meter, and for an orifice meter, comparison of the coefficient of discharge for an orifice meter and a venturi meter, and they have given four conditions which can be out of which one can be true, one is true. So you have the option A as uncertain and can have any value, B, equal to the coefficient of discharge of venturi meter, so and C, more than the coefficient of discharge of venturi meter, Option D, less than the coefficient of discharge of venturimeter. So in this case, the answer is option D. There will be less than the coefficient of discharge of venturimeter. CD is from the expression for a flow rate, you get expression in terms of velocities and pressure differences, and velocities, pressure differences, densities, and so on. In that, you multiply with a constant CD, which depends upon the type of flow meter which you use. And for this, the orifice meter is just a simple plate, while a venturi meter, you have a decrease in area and then an increase in area. So you have a throat section in venturi meter, and either side your area reduces and decreases. In this case, orifice meter, you can have an idea that there will be more losses in orifice meter, so it will the CD will also be less. CD is kind of an efficiency, kind of, you can think in that sense, so it will be easier to understand. So CD for orifice meter will be less compared to the venturi meter. So option is option answer D. In moving to next question, we have, in a venturi meter, pressure at the throat is. So we asked, in a venturi meter, pressure at the throat is less than the entrance pipe pressure, greater than the entrance pipe pressure, C equal to the entrance pipe pressure, and D independent of the rate of flow. So our venturimeter, as I already mentioned, venturimeter is one where you have a pipe. If you assume a pipe is of diameter D, so it will reduce from that diameter to a small throat diameter, which is less than the diameter of the pipe, and then it will start increasing again. So in this case, you flow occurs, you measure the pressure difference between the entrance and the throat section, and you can estimate the flow rate. So in this case, they asked what will be the pressure at the throat. So the pressure at the throat will be option A, less than the entrance pipe pressure. Why this happens? So you have, if you see Bernoulli's equation, or you do an pressure energy balance, so you will get P by rho plus V square by 2 equals is constant. So pressure uh, and you have a velocity term, so that will be equals to constant. So if the pressure reduces, your velocity will go up. So in this case, when the pressure reduces, your velocity will go up, and as the diameter reduces, you have as the flow is constant, or your mass flow is constant, your q will be area into velocity. So as the area reduces, your velocity should go up. So in that sense also, you can remember, when the area reduces, your velocity should go up for a constant flow rate. So when the velocity goes up, your pressure will automatically come down from the Bernoulli's equation. So in this case, we are assuming that the venturimeter is put horizontally, so z term, potential terms are cancelled out. So you have pressure term and a velocity term, p by rho plus v square by 2 equals constant. So in this case, we have seen that velocity goes up when the area reduces, so that in which cause the pressure to reduce at the throat section. Or else you can remember, physically, your velocity when the fluids are moving at a faster rate, it has less time to exert pressure on a section. So pressure is basically the fluids exerting force on a point. So when they are moving, they have less time to exert that pressure. So that also you can physically, you can remember that the pressure will go down. So option is option A, less than the entrance pipe pressure. So moving on to next question, we have a pitot static tube measures. A pitot static tube measures A, static pressure, B, dynamic pressure, C, total pressure, and D, differential pressure. So this question we ask, a pitot static tube we will measure what? So we have A, static pressure, B, dynamic pressure, C, total pressure, and D, differential pressure. So the answer is for this is option B, dynamic pressure. So your pitot tube is basically you have an L type tube of a smaller diameter. You put it in term flow. What that does is you that will measure the static pressure at that point. So you have a fluid flowing at some pressure P and also has some velocity. So the total pressure is the pressure of the fluid plus the velocity, the pressure due to the velocity. So if you bring that fluid to rest, what will be the pressure? That is the static pressure. So if you bring the velocity to zero, that will be your static pressure. So that, and because also you measure the pressure at that point. So the difference will give you the dynamic pressure. The dynamic pressure is purely the pressure due to the fluid's velocity or the flow. So that is called the dynamic pressure, and the pitot static tube measures the dynamic pressure. The difference in the pressure and the static pressure will give you the dynamic pressure. So pitot static tube will measure option B, dynamic pressure. So the next question is, of the various methods of measuring discharge through a pipeline, the one with the least loss of energy and direct reading is by means of option A, transversing a pitot static tube, B, orifice meter, C, venturi meter, option D, notch. So we have been asked to specify which type of measurement will give you least loss in energy and a direct reading. So in this case, you see the out of the four, venturi meter will consume the least amount loss of energy, will cause least loss of energy compared to the others. So the answer is option C, venturi meter. So the next question is, the lowest temperature limit of mercury in glass thermometer is? So the lowest temperature limit of mercury in glass thermometer is option A, minus 200, option B, minus 80 degrees Celsius, option C, minus 35, and option D, minus 50. So the answer is option C, minus 35 degrees Celsius. So the reason being, the freezing point or the melting point of the mercury is close to minus 40. So it will start freezing. So we cannot measure the displacement or change in the volume of the mercury. So and you have some what do you call safety factor, you put in another 5 degrees, so it can measure from minus 35 degrees Celsius. The lowest it can measure is minus 35 degrees Celsius. So it's limited by the fluid or the metal mercury which is in liquid state. It's limited by its freezing point or melting point, which is minus 40 degrees Celsius. So the answer is option C, minus 35 degrees Celsius. So the next one is, which of the thermocouple can measure temperature in a comparatively high range? So which of the thermocouple can measure temperature in a comparatively high range? This answer is sorry, I didn't remove this, so the answer is wrong here. It's not B, so it's something else. So which of the thermocouple can measure temperature in a comparatively high range? Option A, iron constantan; B, copper constantan; C, chromal aluminal; D, tungsten molybdenum. ஹலோ, கிளாஸில் இருக்கேன், என்னாச்சு? சும்மா தானே. சரி, நான் அப்புறம் அடிக்கிறேன். So which of the thermocouple can measure temperature? Sorry. Which of the thermocouple can measure temperature in a comparatively high range? So you can see it's option D, tungsten molybdenum. So tungsten can withstand high temperatures, so it's fairly easy to remember in that sense. So thermocouple is option D, the tungsten and molybdenum. That thermocouple can be used for high range temperature measurements. Moving on to the next question. A parallel combination of thermocouples is used for the measurement of option A, small temperature difference between the junction; option B, large temperature difference between the junction; option C, average temperature difference between the junction; and option D, none of the above. So we have been if you use a parallel combination of thermocouple, it's called a thermopile. So you have if you assume you have a copper constantan type thermocouple. So if you connect all coppers and all constantan, so that gives you a parallel combination. So if you put copper constantan and you connect another thermocouple of copper to this the constantan of thermocouple 1 and copper of thermocouple 2 is connected, so dissimilar metals are connected together. In that case, it will form a series connection. A dissimilar metal combination will give you series connection, and a similar metal connection will give you a parallel combination of so in this case, if you combine thermocouples in a parallel combination, so what type of measurement will you get? Will you get a small, is it used for a small temperature difference, or a large temperature difference, or an average temperature difference? So in this case, answer is option C. You get average temperature difference. So to get an average temperature difference, use a parallel combination. So moving on to the next question. Which of the following metal is to be preferred in a resistance thermometer employed for measuring temperature in the range of -200 to 1000 degrees Celsius? So which type of metal can be used to for in a resistance thermometer for temperature of -200 to 1000? So option A, platinum; B, copper; C, nickel; and D, tungsten. So for a temperature measurement of -200 to 1000, you can use option A, platinum. So platinum will also give you a linear trend, and this tends the resistance type is RTDs, resistance temperature transducer. So you can use a platinum to measure to a range of 1000 degrees Celsius. So moving on to the next question. Self-compensating capillary tube is used in the filled-in system thermometer to eliminate or minimize. So self-compensating capillary tube is used in filled-in system thermometer to eliminate or minimize. Option A, elevation effect; option B, immersion effect; option C, barometric effect; option D, temperature effect. In this case, a self-compensating capillary tube is used in the filled-in system thermometer to eliminate or minimize the temperature effect. So to minimize the temperature effect, we use a self-compensating capillary tube. So the next question is, the bending of bimetallic strip during rise in temperature is due to difference in their A. coefficient of linear expansion, B. elastic properties, C. thermal conductivities, option B. none of these. In this case, uh, the bending of bimetallic strips, so bending action is caused due to rise in temperature. So what causes this? Is it coefficient of linear expansion, B. elastic properties, C. thermal conductivities, or D. none of these? So bending of bimetallic sticks happens due to coefficient of linear expansion. So coefficient linear expansion, your length of or length, if it's of length L, so the length will increase by some amount due to the temperature. So bimetallic strips are two metallic strips bonded together. So each will have a different linear expansion coefficient. So that will cause it to expand or increase in length with of different lengths. So one extending it to different higher length and to from the compared to the other, and this being bonded together, it will cause a bending action, and so that bending of bimetallic strip is caused due to the coefficient of linear expansion, and this being different for the two metals. So the answer is option A, coefficient of linear expansion. So next, moving on, we have a vortex flow meter which uses a shedder having a Strouhal number of 0.20. Estimate the mean duct velocity. The shedding frequency indicated is 77 Hz, and the shedder characteristic length is 1.27 centimeter. So in the problem, they have mentioned that we are using a vortex type flow meter, and which also has a shedder at its end, and that shedder has a Strouhal number of 0.20, and the shedding frequency, or due to the flow, the shedding frequency is 77 Hz, and the shedder which is used as a characteristic length of 1.27 centimeter. So in this case, we are asked to calculate the mean duct velocity. So in this case, if you see, the known are, you know, Strouhal number, we know the frequency of shedding, and then also the characteristic length, which is 1.27 centimeter. The Strouhal number is defined as shedding frequency into characteristic length by mean velocity of flow. So from this, we know Strouhal number, we know shedding frequency and characteristic length. The only unknown is the mean velocity of flow. So we can find mean velocity of flow by substituting the values. So the shedding frequency 77 into your characteristic length converted into meter, Yeah, 1.27. So divide by 100, you will get a 0.0127 meter. Divide by the Stokes number is zero point 0.2. So we get 4.89 meters per second. So that is the mean velocity of the flow, which has been asked, mean duct velocity of the flow. So moving on to the next question, we have a thermal type mass flow meter. A thermal mass flow meter is used to meter 30 degree Celsius air flow through a 2 centimeter inner diameter pipe, ID pipe. If 25 watt of power are required to maintain a 1 degree Celsius temperature rise across the meter, estimate the mass flow rate through the meter. So Cp is given 1.006 for the air. So what is in this case, you have a duct and you need to measure the flow in the duct. So you are using a thermal type mass flow meter. So, and the air which is entering the duct is at 30 degrees Celsius. The diameter of the pipe is 2 centimeters. The inner diameter is 2 centimeters, and the thermal type anemometer or the mass flow meter, it's maintaining a temperature difference of 1 degree Celsius across it. So we know the temperature difference in the thermal mass flow meter is 1 degree Celsius, and the power consumed for by the thermal mass flow meter is 25 watts. So it's being electrical type heater. You are measuring 1 degree Celsius and you're using a 25 watts of power to maintain 1 degree Celsius temperature rise across the meter. So, and estimate the mass flow rate through the meter. So we are asked to find the what will be the mass flow rate across the meter. So we have given that specific heat of air is 1.006 kilojoule per kg per Kelvin. It's a simple problem. We can use an MSc balance to calculate mass flow rate. So in this case, we are using a thermal type measurement, and we have been given the inlet conditions for air as 30 degrees Celsius. Cp is given 1.006, and we also know that inner diameter of the pipe is 2 centimeter. You know the power consumed by the thermal mass flow meter, and the temperature difference is 1 degree Celsius. So 30 degrees Celsius for airflow, diameter, inner diameter given is 2 centimeter. You know power 25 watts. Delta T, temperature difference is 1 degree Celsius. You know Cp 1.006 kilojoule per kg Kelvin. So power supplied is the power supplied of 25 watt will be fully dissipate to the fluid. The air will consume the total of energy which has been given to the thermal mass flow meter, and it will increase its internal energy by so it's increasing it by 1 degree Celsius. So we know, so the mass into Cp into delta T is the change in the internal energy of the air, and that is equals to the power consumed by the thermal mass flow meter. So E equals to mCp delta T in this case, and we know E is 25 watts, and so from this we can calculate the mass flow rate of the air. So M is power by Cp delta T. So power is 25 watts divided by the 1006. What was given is 1.006 kilojoule per kg Kelvin. Here we are converted it to joule per kg Kelvin into 1 Kelvin. So that will give you 0.0025 kg per second. Before that, I forgot to mention something. Self-compensating capillary tube. See, in this temperature effect, how do we neglect this temperature effect? What is self-compensating a capillary tube is, you have a to measure pressure. If you suppose use an analog type measurement, you use a Borden gauge tube, and how do you take fluid? You tap a small amount of the fluid using a capillary tube. Capillary tube is just a small thin tube, very small diameter. That is a capillary tube, and the end of it which will have you have a bulb which contains a fluid, and that fluid is bulb is connected to the capillary to the Borden gauge tube. So that is in the environment which where you may want to measure the temperature. So suppose a fluid is at temperature T and you want to measure the temperature, you you inversely calculate based on the pressure, you measure the temperature. So that temperature will cause some increase in pressure of the fluid in the bulb, that will cause an increase in pressure, and that is reflected by the meter. So using that pressure and pressure, you can estimate the temperature. So this temperature, this measurement can be affected by the ambient conditions. So how do you do this? You connect another capillary tube which is exposed to the ambient condition, and so that will taking a differential pressure of this will give you a better results. So that is a self-compensating capillary tube. Having an additional capillary will give you self-compensation, so that will eliminate the temperature effect. So that is a self-compensating capillary tube. So moving on, we have already seen a thermal mass flow meter problem. So we'll move and see a pitot static tube. Pitot static tube is used to measure the velocity of an aircraft if the air temperature and pressure are 5 degrees Celsius and 90 kilopascal respectively. What is the aircraft velocity in kilometer per hour if the differential pressure is 250 mm of water column? So the density of water or the manometric fluid liquid is given as 999.8 kg per meter cube. So in this case, we know a pitot type static pitot static tube is used to measure the velocity of the aircraft. So the conditions are given as air temperatures as 5 degrees Celsius and 90 kilopascal pressure, and the differential pressure is 250 mm of water column, and we need to find out the aircraft velocity. We have also been given the density of water. So in this case, if you see, we know the density of air is 5 degrees Celsius, which is 278 Kelvin, and pressure is 90 kilopascal. So using ideal gas relation, for a gas constant for air is 287. So from there we can find out the density. So because PV equals to nRT or MRT, and then we can using converting R from universal gas constant to the R of fluid using the molecular weights and so on. So you get P equals to rho RT, and then if you substitute, we know P, we know temperature, we know the gas constant. So after substituting, we will have 90 into 10 power 3 is kilopascal from Pascal. We're converting it to Pascal, and then we know R287. We know R287, and temperature is 278. If we substitute the values, we get the density values is 1.128. Sorry, I'll come back. I'll brief you the problem. We have a pitot static tube. We want to measure the velocity of the aircraft. So the condition we given is the temperature and the pressure are 5 degrees Celsius and 90 kilopascal, in which the aircraft is flowing, and the aircraft velocity is to be calculated. The differential pressure across the pitot-static tube is given as 250 mm, and the density of pressure is in 250 mm water column, and the density of water is 999.8 kg per meter cube. So in this case, we have at the start we are calculating the density from the pressure temperature using the ideal gas relation, and then we know the differential pressure is given as 250 mm of water column. So that is rho into gh. We know manometric fluid density is already given 999.8 into g 9.8, and from 250 mm to converting it to meter, it's 0.25. So we know the differential pressure is 2446.8 Pascal. So from pitot tube, as it measures the dynamic pressure, so dynamic pressure is V square by 2 rho, V square by 2, and you know the dynamic pressure we have already calculated, it's as 2446.8. So using V equals to root of 2 delta P by rho, we measure the velocity of the aircraft. So in this case it's 65.87 meter per second, but in the problem they have asked it to in terms of kilometer per hour. So converting it to by kilometer by multiplying 1000 by 3600 and so on, we will get 237.1 kilometer per hour. So this is the velocity. So in this case we have assumed that the velocity, the aircraft is not, the fluid is not compressible, so it's an incompressible fluid. So we'll check whether that assumption is good. So if it's not good, we have to use a compressible flow relation. So in this case, for specific heat of ratio of specific Cp by Cv is 1.4 for air, and your the speed of sound is root of gamma p by rho. So you can use gamma RT also. So in this case, root of gamma p by rho. So gamma is 1.4. You know the pressure, and we also know the density. We have already calculated that. So in this case, the speed of sound is 334.2 meter per second, and our velocity is 65.87 meter per second. So using that, we see that Mach number is 0.197. So this being very low Mach number, so we can assume that the incompressible flow assumption is holds good. I hope this is clear. Okay, so moving on to the next problem. We have a pitot static tube is used to measure the velocity of water flowing in a pipe. The water density is 1000 kg per meter cube. It's known to have a velocity of 2.5 meter per second. So where the pitot static tube has been introduced, so the point at where the pitot static tube is used is the velocity at that point is 2.5 meter per second, and the static pressure is measured independently at the tube wall and is 2 bar. What is the head developed by the pitot static tube if the manometric fluid is mercury with density equal to 13,600 kg per meter cube? So we have to find out the head in terms of mercury column, and we have been given that the fluid flowing is water which has a density of 1000 kg per meter cube, and the velocity is 2.5 meter per second, and we have also been given that the static pressure is 2 bar. So we'll see how to solve this problem. So we know static pressure is a 2 bar, which is already given. The dynamic pressure is rho v square by 2. So rho is given as 1000 for the fluid flowing, density of the fluid flowing is, which is water, 1000 into velocity is also is known, 2.5. So substituting that, we get 3125 Pascal. So head developed is the static. In this case, we the pitot static tube will measure the dynamic pressure. So that's known. So pitot, we the head developed will be just the head of the dynamic pressure. So PD by rho m by minus rho into g. So rho m minus rho is just conversion for from water column to the mercury column. So using that relation, we get dynamic pressure. We already calculated 3125 Pascal, and we know the mercury column density is 13,600 and the fluid density. Substituting that, we get 0.02531 meter, so or 25.31 mm of Hg. So in a mercury column, we'll get 25.31 mm. So the static pressure is actually not needed. It's just to confuse you to which pressure to be used. So we have to remember that the pitot static tube will always measure the dynamic pressure or just the pressure caused by the fluid velocity. So moving on to the next question. We have a hot wire which operates at a temperature of 200 degrees Celsius, while the air temperature is 20 degrees Celsius. So the velocity of air may vary between 0 and 10 meter per second. The hot wire element is a platinum wire of 4 micrometer diameter and 1.2 mm length. So a hot wire is there in the flow, which is operating at a temperature of 200 degrees Celsius. The air temperature is 20 degrees Celsius. So the velocity of air is varying between 0 and 10 meter per second. It may vary between 0 and 10 meters per second. The hot wire element is a platinum wire. So you have a platinum wire of 4 micrometer diameter and 1.2 mm length. So what is the sensor output when the air velocity is 4 meter per second? We have given that electrical resistivity at 20 degrees Celsius is 10.5 into 10 power minus 8 for per degree Celsius. And we have also been given a Nusselt relation, what TW is T wire by the fluid temperature raised to 0.17 into 0.24 plus 0.56, Reynolds number raised to power 0.45. So we'll see how to calculate this problem. So in this case, we need to find out sensor output, or the value which the sensor gives, or the voltage. So the sensor will convert this and give you output in terms of voltage. So you have to measure that. So we know that the diameter of the wire which is used, the platinum wire, is of length 4 micrometer and 1.2 mm length. So we know D is 4 into 10 power minus 6 and length is 0.0012 meter. And you also know that electrical resistivity, so rho naught is given. We find out R naught, the resistance, so which is L rho naught by pi d square by 4. So that will give you 10.03 ohms. This should be in ohm meter per degree Celsius. I'll make a change here. So we know resistance. So the resistivity at any temperature is given as rho naught 1 plus alpha T minus 20 and so resistance of wire is Rw R naught 1 plus alpha into T minus 20. We know resistance, we have already calculated resistance at the reference point. So R naught is 10.03 and 1 plus alpha value for platinum is 0.00385 into 200 minus 20. which will give you 17.1 ohms. So the mean temperature for calculating the Reynolds number, because we are the uh, the platinum wire is at 200 degrees Celsius and the fluid is at 20 degrees Celsius. So we use at mean values to calculate the fluid properties. So for a mean value of 110 degrees Celsius, we get nu or dynamic viscosity as 24.15 into 10 power minus 6 meter square per second, and uh, your thermal conductivity is 0.032 watt per meter degree Celsius. So from this Reynolds number is Vd by nu. Uh, so we have velocity, which is we are assuming it's varying from 0 to 10 meters per second. So we assume V is 4. So 4 into 10 power minus 6 divided by 24.15 into 10 power minus 6. So we get Reynolds number of 0.663. So we substitute that value in the Nusselt number relation. We know the temperature of wire, which is we take a mean temperature 110 plus 273, and the fluid is 20 plus 293. So using that, we get Nusselt number as 0.738. We also know that Nusselt number is Hd by K. H is thermal heat transfer coefficient into diameter divided by thermal conductivity. So we calculated Nusselt number. On substituting, we get heat transfer coefficient as 5906 watt per meter square degree Celsius. In this case, it's degree Celsius. So, and then because the thermal conductivity is given in degree Celsius, so from there we calculate Q as pi d LH into T minus 20. So we substitute pi, and then we also substitute the known values d, L and H. D is 4 into 10 power minus 6, it's not 10 minus 6, 10 power minus 6, into L is 0.0012 into 5906 into 200 minus 20, which will give you 0.016 watt. So this will equals to the power supply to the platinum wire, which will be equals to V by Vi or V square by R. So E is the voltage, so E square by R of wire. From there we can find out the voltage, which is equals to root of the heat flow and then into resistance of wire. So that will give you 0.016 into 17.1, which will give you 0.524 volts. So the sensor output will be 0.524 volts, and this may vary with respect to the Reynolds number, but for different velocities. So moving on, consider water flowing in a pipe of 100 mm diameter at a velocity of 1 meter per second. The angle theta has been arranged to be 45 degrees. Discuss the case with ultrasound TO of velocity measurement point of view. And we have given the speed of sound is 1500 meters per second. So you have a water flowing in a 100 mm diameter pipe with the flow of water is at a velocity of 1 meter per second. So the transducer is kept at an angle of 45 degrees Celsius with ultrasonic TOF, and you have a receiver, and then it's reflected and it's again picked up by the transducer. So by the receiver, so you have two measurements, and using that you have to calculate the velocity. So we have to discuss what type of ultrasound is to be used. So we know C is 1500 meters per second. We know the diameter of the pipe is 100 mm, which is 0.1 meter, and the angle at which the transducer is kept is 45 degrees Celsius, and the velocity is at 1 meters per second. So in this case, the length of travel of the ultrasonic wave is will be d by sine theta. So it will be cross line, it's not a straight line. So as it's kept at 45 degrees Celsius, so the length will be d by sine 45, which is 0.141 meters. From this we can estimate the time it takes to uh, reach from the transmitter to the pipe and then again back to the receiver. So in halfway, that is, we know the distance traveled is 0.141, and the velocity, the relative velocity will be v plus the speed of sound of the wave, which is 1500, plus v into cos 45. So the relativity velocity is c plus v cos 45. So we substitute the values. Cos theta is 45 degrees here, so we get 954.236 microseconds. Again, the one for velocity going up back will be the relative velocity will be c minus v cos 45. So there is plus, here it's minus. Here the temperature will be 94.325 microseconds. So the difference in time it will take is uh, 0.089 microsecond or 89 nanoseconds. So in this case, we need a very accurate temperature measurement, or the transducer which can measure a very small time second, which is highly sensitive. So that kind of ultrasound should be used. So moving on, we have platinum resistance thermometer is used at a room temperature. Assuming a linear temperature variation with resistance, calculate the sensitivity of the thermometer in ohms per degree Fahrenheit. So we need to calculate the sensitivity of a platinum resistance thermometer used at room temperature. So we know the relation for the resistance thermometer is, it varies linearly as R naught the reference temperature into 1 plus alpha T minus T naught the reference temperature. T naught is reference temperature, R naught is resistance as the reference temperature. We know that sensitivity is uh, uh, resistance divided by temperature, or differentiation of resistance with respect to temperature. So that will give you, if you differentiate the relation with respect to temperature, we'll get alpha R naught. So the sensitivity for the platinum resistance thermometer is alpha into the reference temperature, reference resistance. So moving on to the next question. Calculate the temperature sensitivity for thermistor number 1 in figure at 100 degrees Celsius. Express the results in ohm centimeter per degree Celsius. Take beta as 4120 Kelvin at 100 degrees Celsius. We have a thermistor, and a graph is given which gives you a specific resistance ohm centimeter to with respect to the temperature, and we need to calculate the temperature sensitivity for thermistor 1. So we have the first curve, we have to use that, and the resistance relation is given as R naught exponential beta 1 by T minus 1 by T naught. As we know, the sensitivity is differentiating R relation with respect to temperature. The sensitivity relation is R naught exponential beta, this being exponential, we get as it is, and differentiation of the inner bracket term will give you minus beta by T square. The 1 by T is minus 1 by T square, and beta as it is. So this is the sensitivity relation for given is at 100 degrees Celsius is the reference temperature. So from curve for 100 degrees Celsius, it's somewhat more than 110 square, so we assume it's 110. So using that, so resistivity is known, so R naught exponential beta, that term is known, so that is minus 110 into 4120 is the beta values which is given, divided by T square 373 whole square. So that will give you minus 3.26 ohm centimeter per degree Celsius. So that is the sensitivity. So moving on, we have a problem for thermocouple. An ion constant thermocouple is connected to a potentiometer whose terminal are at 25 degrees Celsius. The potentiometer reading is 3.59 millivolts. What is the temperature of the thermocouple junction? So we have a ion constant thermocouple, and we have a table which gives you voltages corresponding to temperatures. So EMF generated due to the temperature is given, and we have also been given that the ion constant thermocouple is used, which is connected to a potentiometer, and the potentiometer terminal is at 25 degrees Celsius. The potentiometer reading which it shows is 3.5 millivolt. What is the temperature of the thermocouple junction? So what will be the thermocouple junction? So you have a thermocouple and the junction temperature is 25 and the potentiometer which is going 3.59. So at that temperature will be summation of the EMF generated by 25 degrees Celsius and the potentiometer reading will be the EMF generated at the temperature of the junction. So EMF at 25 degrees Celsius is obtained as 1.27 millivolt. So from the table, that for 25 for ion constant is 1.277. So we substitute that, and we know that the temperature EMF is the junction temperature at the potentiometer plus the potentiometer reading. So will give you 1.277 plus 3.59, which is the potentiometer reading, will give you 4.867 millivolts. So that is the EMF generated for the temperature at the junction. Using this 4.8767 for ion constant, you can see it lie between 75 and 100. So using interpolation, we calculate that the corresponding temperature is 92.5 degrees Celsius. So that is the junction of the temperature at the junction of the thermocouple. So moving on, we have 4 ion constant and thermocouple junction which are connected in series. So you have 4 ion constant and thermocouple junction. So 4 junction A, B, C, D, and these are connected in series. So this is one metal, this is another metal. So this is being ion constant, assuming that ion is connected to the your voltmeter or potentiometer, and that you have a junction between ion and constant, and this constant will again be connected to another ion piece, and then a constant and then an ion. So you have 4 junctions here. So if you use another metal, and this being potentiometer being of different material, there can be another junction form. So you're using a same material here to connect the potentiometer to ensure that you have only 4 junctions A, B, C, D, and they have given that the 4 junctions are at temperature of 200, 300, 100 and 32 degree Celsius. Sorry, this is in Fahrenheit, 32 degree Fahrenheit. So calculate the EMF indicated by a potentiometer. So in this case, we know that we have 4 junctions. So the first ion is connected to the potentiometer. So this being positive, the EMF generated, this will become negative. And you have another connection, this being a ion and then a constant, and now a constant and an ion is used for junction B. So this EMF generated will be negative. So this will act in different action, because you have ion at positive, constant will be negative, and then again ion positive. So EMF will be EA. It will be EMF will be EA, and then will be minus EB. Then you have EC positive, and then ED negative. So EMF will be summation of all this. So E will be EA minus EB plus EC minus ED. So on substituting the values corresponding, EMF generated corresponding to the temperature of 200 degree Fahrenheit, 300 degree Fahrenheit, 100 degree Fahrenheit and 32 degree Fahrenheit, we get 32 degree Fahrenheit is 0 degree Celsius. So from table you can see it's all 0, because 0 is being the reference temperature used here, and the corresponding temperatures, if you calculate converting it to degree Celsius and finding the EMF, on substituting we'll get E is plus or minus 1.09 millivolts, which is used the calculate the EMF indicated by the potentiometer. So the potentiometer will indicate 1.09 millivolts. So that's all for today. As there are no other queries, I will close the session. Thank you.